or CNNs, excel in processing visual information. Inspired by the visual cortex of the brain, CNNs use convolutional layers to extract features from images, making them highly effective for tasks like object detection, image segmentation, and facial recognition. Generative adversarial networks, or GANs, consist of two competing networks, a generator and a discriminator.
While deep learning has achieved remarkable progress, several challenges and limitations need to be addressed to unlock its full potential and pave the way for artificial general intelligence, or AGI. These challenges stem from the data-driven nature of deep learning, its computational demands, and the interpretability of its decision-making processes. Deep learning models typically require massive amounts of labeled data for training, which can be time-consuming and expensive to acquire. This reliance on large datasets poses a significant challenge, especially in domains where labeled data is scarce or difficult to obtain. Training complex deep learning models, particularly those with millions or even billions of parameters, demands substantial computational resources. Despite their impressive performance, deep learning models are often considered black boxes due to the difficulty in interpreting their decision-making processes.
Despite the challenges, the field of deep learning is constantly evolving, with ongoing research and advancements pushing the boundaries of what's possible. Researchers are actively exploring novel techniques to address the limitations of deep learning and unlock its full potential. Transfer learning, a promising area of research, aims to leverage knowledge gained from one task to improve performance on a different but related task. This approach can reduce the reliance on large datasets by allowing models to benefit from pre-training on related tasks. Researchers are developing more efficient deep learning architectures and training algorithms to address the computational demands of deep learning. Techniques like model compression, pruning, and quantization aim to reduce the size and complexity of deep learning models without sacrificing performance. The future of deep learning is brimming with possibilities, poised to play an even more transformative role in our lives, driving innovation, solving complex problems, and shaping the future of artificial intelligence.